Yeah, be careful here. What did you watch growing up?
What did I watch growing up? Like for a time we watched Voltron.
Voltron, okay.
Yeah, Voltron, you know, Defender of the Universe and all that. He-Man for a time.
He-Man.
Let's see here, what else do we watch? I've seen a little bit of Thundercats, not too much.
Thundercats was fire.
You know, Thundercats, Ho, yes. Of course the classics like Merry Melodies, you know, Bugs Bunny, the Roadrunner, all that stuff, you know, classic cartoons. Woody Woodpecker, Popeye, but only if there was nothing else to watch.
Did you guys have like an Atari?
No, we did not have an Atari or a Nintendo. My mom would definitely not have allowed that. She didn't care for video games. She thought that they were rotting the mind, and I think she's right. But
at least did you watch, like, were you watching, I know you mentioned Naruto a lot in like your exams, did you watch that growing up or when you got older?
When I got older, like I started watching Dragon Ball Z when I was in like college.
Okay.
That came out in like the late 90s on the Cartoon Network or whatever.
Yeah.
But yeah, we'd all watch Dragon Ball Z when I was like in college.
Was Naruto put in Naruto too, right?
Naruto came after that.
Yeah.
So I watched Naruto when I was like, I don't know, 2005, 2010, somewhere in there.
I watched it 2 years ago.
But anyway, I will begin with a word of prayer. As this is not helping you with anything except for general Dr. Cook trivia, which is never really tested on. It should be.
It's never really tested.
I'll begin. Dearly Father, we thank you for this day. I thank you for these students. Just ask that you just bless our work today. Help us to just understand a little bit more about how to solve and interpret differential equations. Lord, in your name I pray, Lord Jesus. Amen. So let me start with the easy example that I missed last time. So example 1. So suppose you're going to solve, well, I guess I don't need to look it up. Something like y prime prime plus y prime equal to 0. Suppose you wanted to solve this differential equation. Now it's second order, right? So that means we can't just do separation of variables. There's something sneakier is involved. So basically, to look at this a different way, we're going to let y prime equal to v. All right, so basically make a velocity substitution, all right? And with that velocity substitution, the original differential equation becomes what? What's y prime prime?
V prime.
Yeah, y prime prime is v prime. I'll write it in a different notation. So what that gives us is dv, let's say dt, all right, plus v equals to 0. And that is pretty easy to solve, right? Like we can separate and integrate. Let's do it. So we've got, dv dt equals to minus v, and then that gives me dv over v equals to minus dt. Integrate both sides, right? I get the natural log of the absolute value of v equals to minus t plus, let's say, c1. And then I'll solve for v by exponentiating both sides, right? So exponentiate both sides, we get e to the natural log absolute value of v equals e to the minus t plus c1, which we can rewrite as e to the c1 e to the minus t by laws of exponents. And then that gives me that the absolute value of v is equal to, of course this is, allow me this short manga style calculation here. There we go. I'm sorry, manga style. What's wrong with me? But there we go. Anyway, so this is going to give us that v is equal to plus or minus e to the c1 e to the minus t. All right. So we might as well just label that constant something relevant, right? Like what happens when you put t equals to 0? What happens to this equation? We get v of times 0, right, whatever that is equal to plus or minus e to the c, 1, right? So we might as well label the constant plus or minus e to the c1. We might as well just label it v sub naught, right? Where v sub naught is, kind of a standard notation, typical notation for the velocity at time 0. That's not written in stone, but you know, a lot of your more evil physics professors use that notation. So that gives us v is equal to v0 e to the minus t. Now we're not done, right? At this point, we've just found the velocity as a function of time, assuming what? Interpreting things here, right? I'm assuming then, if I say that, I mean to say then that y is the position of some particle. The derivative of the position is the velocity, right? So if that's the case, that's the velocity as a function of time for this problem. Now how do I find the position if I found the velocity? I just integrate it, right? So that would be dy dt. We have to integrate that thing, yeah? So that's not hard. That gives us y is equal to, let's say, minus v naught e to the minus t plus c2. All right, I'll write it again up here. So we have y equals minus v naught e to the minus t plus c2. Now my question is how to express c2 in terms of the initial position y of 0. Let's call that arbitrary constant y sub naught. So I mean, all I do would be plug time 0 into the equation, see where it takes me, right? Plug time 0 into that, what happens? So y of 0, what happens with this term when you plug time 0 into it? You just get back what? Minus v sub naught, right? Because e to the 0 is 1. And then plus c2, yeah? And that's all equal to y sub naught. So apparently, c2 is y sub naught plus v naught. And we can write the equation for the motion as follows. Y is equal to, apparently, y naught plus v naught minus v naught e to the minus t. Or if you like, we could rewrite this a little bit better. Y is equal to the initial position plus the initial velocity times 1 minus e to the minus t. And there you go. That's a pretty nice formula for the solution in terms of the initial conditions. Now, I don't think I did all this in the notes. Like if you look at the notes where I did this example, I probably didn't go to the trouble of fitting initial conditions, right? If you look at page... Oh, wow. Oh, I just did a really different problem. Example 5.7 is just different. Huh. Interesting. I mean, we could do that one next if you guys are interested, but let's see here. Any questions about this one before I forge ahead? Yes, sir.
Did you not ever substitute the y prime prime and y prime back in for v?
Y prime prime and... So my initial substitution was y prime equals to v. Did I substitute it in? I did, but you just have to kind of look at it. This right here, right, is y prime prime plus y prime, right, equal to 0. But that is v prime, and this is v. So it's right here.
Yes, sir. But like after you worked it out,
Oh,
the y prime.
right here.
That's what. Okay.
I set v equal to dy dt again, and then we integrated to get to here.
Then how'd you end up getting the v naught like in the?
That was right here. I just labeled plus or minus e to the c1 as v naught.
Okay.
After we noticed that if we plug time 0 in, this just becomes v of time 0 is plus or minus this constant, whatever it is, because e to the 0 is 1. Yeah?
For all the double prime and single prime equations, are we going to have to use like the y naught and the v naught to properly solve it?
It depends on the instructions. Like if it said write the solution in terms of initial conditions, then yeah. If it doesn't, if it just says find the explicit general solution or just find the general solution, then you could stop differently. Here, let's do another one where you don't have to do it. So this one, for example 2, this one will not be like that if we had y prime prime plus y prime equal to, let me try to follow my example. This is 5.7. X squared equals to x squared, as it turns out. All right, so we can try this one. All right, so we'll let v equal to y prime again. So v prime is y prime prime, right? And so what we're up against is v prime plus v equals to x squared. Now, I prefer to use the differential notation, so let me rewrite that in the differential notation because that's what I've been using primarily in here. So this is dv dx plus v equals to x squared. So this time, x is what? X is the independent variable, right? In my example 1, t was the independent variable, so it's a little different. How do we solve this problem? This is, what is it? Yeah, the integrating factor method, right? This is a linear differential equation, and the integrating factor method is the way to go. So basically compare this to, the form, remember we had like dy dx plus py equals to q. That's the pattern. It's like this, right? With v going to y going to v, right? And my p is what? By identification, p is 1. What's q? X squared, right? So that's the pattern. That's the pattern. And so I'm going to calculate the integrating factor as the exponential of the integral of 1 dx. Well, that's a pretty easy integrating factor to calculate, right? The integrating factor is just the exponential function. It's kind of non-eventful, e to the x. So we multiply the differential equation by e to the x. What happens? We get e to the x times dv dx plus e to the x times v equals x squared e to the x. And now the dreaded reverse product rule is upon us. Well, I mean, hopefully it works, right? Let's see here. So is this, search your heart, find it is true. This is d dx of what? Of v times e to the x, yeah? You could say, no, it's d dx of e to the x times v. We do not disagree. You could put the v or the e to the x first. It doesn't matter. They commute, right? And on the other side, we've got x squared e to the x. All right. So, all right, integrate both sides then. And what does that give us? So integrating both sides, we get v e to the x is equal to the integral of x squared e to the x, right? Dx. And that is integration by parts, which I will do on the next board. Integral of x squared e to the x dx. We all know how to do this, I think. Well, if we don't know yet, we should learn. This is dv, this is u. So we have e to the x squared e to the x, right? Minus the integral of u dv, which is in this case 2x e to the x dx. Then next step, I'll make this my dv2. I'll make this my u2. And so what I get is x squared e to the x minus, big parentheses, our friends, 2x e to the x minus the integral of e to the x times 2 dx. And then we do that integral, and voila, here's our answer for this part. X squared e to the x minus 2x e to the x minus and minus gives me plus, right? So plus 2 e to the x, and then plus a constant. Do we need to add the constant? Yeah, we need to add the constant. I'll call that C1. So let's collect our thoughts. What we have at the moment is v e to the x equals to, x squared e to the x minus 2x e to the x plus 2 e to the x. Man, so many e to the x's, yeah? Plus C1. what's next? What's our goal? Our goal is to solve for y, right? So we need to undo. First of all, we need to solve for v, right? That's where we're going. Solve for v. And then we're going to need to undo the substitution, which was y prime, right? V equals y prime. So we're going to have to integrate again before we're done. The next step here is v, which is, of course, equal to dy dx, right? V is dy dx, but it's also equal to dividing this by e to the x. We get x squared minus 2x plus 2 plus c1 e to the minus x. So I just divide it by the integrating factor here. Divide by e to the x to get to that. And one more step and we'll be done. Yep.
I was just going to ask, how do we know what to put in the exponential thing where you set I?
It's the whatever p is. So the integrating factor method says you set up the exponential as, the integrating factor rather, is the exponential of the integral of p dx. So that's what you have to learn and apply here. So the p here was 1. The coefficient of the dependent variable v was just 1 in this case. Like I said, I'm matching this pattern, you know. So we're almost done. Now we just, one more step, right, and we'll have y. We've got dy dx equals to that, so we just need to integrate one more time. What happens? Integrate both sides. We get y is 1/3 x cubed minus 2, well, just minus x squared, right? Plus 2x minus c1 e to the minus x plus c2. So there you go. That's the explicit general solution in this case. And I'm not sure that's how I wrote the answer in the notes. Let me take a look. I think I might have written it differently. Huh. Huh. Well, that's interesting. Well, isn't that stupid? All right, so I have solved on the board right now. This is the genuine solution to the problem which is stated in example 5.7. So like there's a typo in example 5.7. Let me explain. So it starts with y prime prime plus y prime equals to x squared, all right? Which we have solved just now, all right? And then in the solution, I say let y prime equals to v, so far so good. Y prime prime is v prime, so far so good. And then I say the differential equation transforms to, I say this transforms to dv dx minus v equals to e to the minus x. Okay, so that is a different problem. I'm solving a different problem in example 5.7. So I think the solution that's there is probably correct for that problem, but it's not the problem which is stated. So what I'm trying to tell you is when you're reading example 5.7, do not be confused. Just understand that you should be like, get to here and say, see lecture notes, which is today, what, what's today? 16? Yeah, okay. See the lecture from 216. This is, I think, solved right there in the notes. All right, so see what this is coming from. This would be coming from y prime prime minus y prime equals to e to the minus x, which is a very similar but different problem. Yeah. I think I did that so that I wouldn't have the integration by parts twice in the example. You know, and then I forgot to edit the original problem when I was typing up the notes. That's what happened. So. Okay, enough of that. You guys have any questions? So at this point, we have reached the applications. Go for it.
Should do the integration substitution because it equals that other equation you remember
I chose to do the,
Like to do integration.
oh, here?
Or dy dx must be.
This, you're talking about this substitution?
No, where you multiply by dx. And
Oh.
you have it equals to dy.
Right, this is our standard solution technique. If we have a linear differential equation, we use the integrating factor technique. That's the way to solve them, usually. There are a select subclass that also allows separation of variables. Like they're not mutually exclusive. There are certain separation of variable problems which are also integrating factor problems, but you know, if you have a linear problem, it will always be solvable by the integrating factor technique. So we just need to watch out for that. Yeah.
What was that like p-plane website you wanted us to use for like solving differential equations?
Oh, did I never posted the, oh, my bad. Yeah, the link is in the notes. Let me see. The, 1 minute here, I'll bring it up. So the notes for the course, right? Like we're currently working through the first order notes, which is the end of my notes. I have to write more notes for you guys somehow. Maybe when I'm sleeping. I don't know. I'm going to try to write more notes for you guys, but we'll see if I don't know. I'm not sure that there's actually enough time in my schedule to make it happen. We may have to fall back on the book. Ugh. Let's see here. Not the book, yes. Did you pay for it though? Let's see here. Oh, well, sorry about that. Let's see here. Come on. I mean, I do have older handwritten notes too, but they're not as, oh wait a minute. You know what? Funny thing, works better if you plug it in. So, in the first order, see this one right here? Oh man, where'd it go? Right there. So these guys, if you open this up, and I think this is also posted in the Canvas, if I remember right. I think I put these in Canvas. Did I put these in Canvas? I might not have. I did not. I see a head shaking. Good.
Do you have the link to this website in your Canvas though?
Yeah. First announcement links to my website, which is where I've hidden all of my things. Let's see here. So in here, if you, oh, yowzers. If you go in here, I actually have like this link right here takes you to the, well, we don't want to go there. That's the GeoGebra page. That's the one that's kind of not awesome. Let's see here, let me go down. I think there's, in this remark right here, that might take us where we want to go. See, this one's okay. This one works? The next link is better? Yeah, this one's not very good. Aw, man, did I just close that? There we go. Go back up. Oh, right here. Is that one? The bottom one? This one? Oh yeah, I don't have a lot of hope. Okay, if this works on this computer, I'll be surprised. Yeah. Sorry, I have the wrong computer with me for this question. This is my Liberty laptop, which is only partially useful. So what I will do, if I remember, which I meant to do already, is I have executable files that will run this thing, and that thing, I'll try to put them in Canvas so you can actually just run those files. You don't even need the website. You can just run the p-plane. It's like a, forget if it, maybe a Java file or something, but you can run those separately. The thing I clicked on a second ago, that will also work. It's just not as nice as the one I was playing with in class originally.
So there's not necessarily one specific one that we need to use?
Oh, no, exactly. So the idea is to create the direction field and use some software that you can click on some points to see the solutions for that problem. So yeah, there's not a unique software to use. And if you can figure out how to, you guys have access to MATLAB. You can just run p-plane in MATLAB. It is a MATLAB toolbox. You can run it there. I don't know how, but it can be done. So, listen, my method for finding computer, I mean, there's also, I'm sure there's also something in Mathematica as well, but you know, other questions that I possibly can't answer today. Sorry about that. Yep.
Could you do another Bernoulli substitution?
Another Bernoulli substitution. Huh. Goodness gracious. That sounds risky. Oh man, too far. Give me a second here. I'm looking for something. Rats. I'm hoping I have another example sitting on. If I just make something up and try to do it, bad things will happen to us. All right, so I'm trying to find an example which is, you know, not so bad. Annoyingly. All right, well, come on. Did we already solve this one?
No.
Hooray! Here's an example. All right, so let me walk us through this one here. Zoom out a bit. So, that was the pattern, right? I think the one I worked in here before had a cube over there. Is that right?
Yeah.
So the example, I'll get back to it here in a sec. Where you go? Where are you going to? Come on. So example 5.5 on page 13 of the article, the first order article. So we're basically looking at remark 5.6 in my notes. And this is the right pattern. We have basically dy dx plus some constant, some function of x equals to x squared times the power of y. When that happens, you make a v equals 1 minus n substitution. So here n equals to 2. And so this means we'll make a v equals 1 over y substitution for this one. If we calculate dv dx directly, like I do here, we get minus 1 over y squared times dy dx. All right. So then that gives me dy dx is, in this case, minus 1 over v squared. That's a little funny. You notice that since they're reciprocal, the no, it's just a direct substitution, duh. So there's dy dx is this. And so I plug that right here. That's dy dx, right? Y over x is what? Y is 1 over v, right? So that becomes 1 over xv. On the other side, I have x squared over v squared. Then I think I multiplied by minus v squared, right? So I brought that to the other side, multiply by minus v squared. That gives me this. Excuse me. So after the dust settles and you make the substitution, you've got yourself to dv dx minus 1 over x times v is equal to minus x squared. Does that make sense? So, and then, well, that's a linear differential equation. So it's then solvable by the integrating factor method. And so I identify my coefficient of the dependent variable is minus 1 over x. So the integrating factor I'm going to calculate by the exponential of the integral of that. The integral of 1 over x is log absolute value of x, but I got a minus. So that brings in a reciprocal power into the log. See, that flips this upside down, which gives me this 1 over absolute value of x. At this point, I realized that I should really have tacked on x greater than 0 to make this problem not so annoying. But this problem has solutions that are separate. Like the solutions for positive x and the solution for negative x are going to be different for this problem. So like the solutions for negative x, you're going to replace x with minus x, essentially. Otherwise, the formulas won't make sense. But anyway, let's assume positive x for this problem. With that doing, I multiply by the integrating factor, the differential equation. What happens then? Then it won't let me scroll down. All right. Let me scroll. Ha, there. Not the boss of me, the boss of you. Take that, computer. All right, so anyway, I multiply by my integrating factor. And then, of course, the dreaded reverse product rule. As always, equals to minus x. Yes?
Third or fourth line from the bottom, is that supposed to be a y or is that a mu?
That's a mu. Oh, yeah, I'm sorry. In the differential equations course, sometimes we use a mu for the integrating factor. That's an artifact of the book that's used for differential equations. But the math is the same. Literally the same here. Same technique. Not a difference. It's just a letter. You can put an I there if you want. Good question. So reverse product rule brings me to this. Then I integrate both sides. The integral of minus x is just minus x squared over 2. I get this, right? Then that gives me v is equal to cx minus x squared over 2. Wait a minute, x cubed over 2. I can't read. See, that 2 becomes a 3 because I multiply by x. And then v was what? Well, v was 1 over y, right? Since v was 1 over y, this is equal to 1 over y, so then reciprocate both sides, and you get y is equal to cx minus x cubed over 2. I stand by my decision to spend 2 minutes to find this problem because whatever I would have made up on the fly here would have been horrible. Because it's very easy to make these problems rather complicated.